Welcome to Lesson 38, where we will explore percent composition. By the end of this lesson, you should be able to calculate the percent composition of a substance and calculate the percent composition of water in a hydrate. Percent composition is very important in distinguishing between pure substances, such as elements and compounds, and mixtures. Mixtures combine two or more. Mixtures are physical combination of two or more substances whose percent composition can vary. A good example are these chocolate chip cookies. All of these cookies are mixtures of sugar and butter and chocolate chips. But because the percentage of sugar and butter and chocolate chips varies, each chocolate chip cookie has different properties, but is still called a chocolate chip cookie. Another good example of a mixture whose composition varies can be seen in these oatmeals. Both of these oatmeals contain a mixture of apples and cinnamon and oatmeal, but the oatmeal to the left has a higher percentage of sugar than the oatmeal to the right, but they are still mixtures of oatmeal. Compounds, on the other hand, always have a constant composition. So carbon monoxide is a compound of carbon and oxygen that has one carbon to one oxygen. If you calculated the percent by mass of oxygen and carbon monoxide, it's 57%. This odorless, colorless, poisonous gas can be distinguished from another compound of carbon and oxygen, carbon dioxide, a less poisonous compound, because carbon dioxide that contains one carbon and two oxygens is 73% by mass oxygen. So different compounds will have different percent by masses of the elements that make them up. Remember, different compounds will have different names and different physical and chemical properties. Percent composition is the percent by mass of each element in a compound. It can be calculated using this equation found on the back of your reference table on table T. Let's do an example problem together. When calculating percent composition, the first step you'll want to do is to calculate the gram formula mass of a compound. This will be the mass of the whole. We'll use our calculation to plug in to the percent composition formula on reference table T. In this example, we would like to calculate the percent composition by mass of calcium in calcium chloride. So the first thing we'll want to do is to use our periodic table to look up the masses of calcium and chlorine so that we can find the gram formula mass of calcium chloride. Now that we have the gram formula masses of each of the elements, we can go and substitute into the formula from reference table T. Adding up the masses of the calcium and both chlorines, we get a total gram formula mass of 111.1. So what we're going to do is we're going to take the mass of the part, which is 40.1 grams, and put that as the numerator of our fraction. And we'll take the mass of the whole, which is 111.1, and make that the denominator. Once we substitute and solve in our calculator, we'll get the percent by mass of calcium and calcium chloride is 36.1%. So by now, you should be able to calculate the percent composition of a substance. A hydrate is an ionic solid where water is trapped in its crystal lattice structure. When writing the formula of a hydrate, you'll see this large dot followed by a coefficient n, which is a whole number of waters that are trapped within each part of the crystal. So for instance, here we have copper sulfate pentahydrate. For every 1 copper sulfate, there are 5 waters trapped within the crystal.
Gonna give you a rent bill. A rent bill, Rachel.
An anhydrate is the vocabulary word that describes a crystal that has no water trapped inside of it. So here you can see a crystal structure, and there are spaces in between where water could be trapped inside. So when water is entrapped inside, the crystal will be heavier and it will have water inside. Therefore, it will be called a hydrate. When the crystal is heated, the water will evaporate, allowing it to lose mass. And then it will be called an anhydrate. As you can see from the picture of the crystal lattice, the spaces in between are able to accommodate water molecules. When water molecules are trapped within the crystal, so the crystal does not feel wet, the crystal will be heavier than it would be if it was heated and the water molecules were allowed to evaporate, thus making it an anhydrate. The silica gel packets that are placed inside of various items are a good example of an anhydrous crystal, a crystal that does not have water trapped inside of it at the beginning of shipping, but can absorb water to keep your items fresh. To calculate the percent composition of water in a hydrate, you're going to have to go and calculate the gram formula mass of the entire hydrate molecule, including all of the waters. And then you're going to have to plug in to the percent composition formula on reference table T. It is important to know that if you heat a hydrated salt, it will evaporate the water, and the difference in the starting and ending mass will be the mass of water inside the crystal. Let's work through this example where we must calculate the percent by mass of water in sodium carbonate. So looking at our periodic table, we can find the gram formula masses of each of the elements. We must also find the gram formula mass of all 10 waters. Notice that the dot in chemistry placed inside of a hydrate formula does not mean times, but it means plus water. So we're going to find the mass of sodium carbonate plus the mass of 10 waters to give a total hydrated mass of 286.1 grams per mole. From here, we're going to go and substitute into the formula. Notice that we must substitute the mass of all 10 waters as our part, divided by the mass of the entire hydrated compound times 100. As you can see, your calculator should give you a percent by mass of 63% water. So by now, you should be able to calculate the percent composition of water in a hydrate. This concludes lesson number 38 on percent composition. Make sure you've taken good notes. They will be checked in class. Write down any questions you have and bring them to class. Complete your homework on Google Classroom and put your Regents Chemistry reference table and calculator back in your backpack so you are prepared for class. I'll see you soon. As a summary, there are two different types of numbers in chemical formulas. There are subscripts, which are small numbers written after an element symbol, and there are coefficients, which are large numbers written in front of the total compound. The subscripts tell us the number of atoms in a formula. Here we have the chemical formula for calcium phosphate. So the first thing we want to do is examine the subscripts so we can determine the number of calcium, phosphorus, and oxygen atoms in the compound. Recall that the subscript 1 is never written but is always understood. So looking at calcium phosphate, you can see that phosphate, the polyatomic ion, is written in parentheses. That means that we actually have 2 phosphate units. 2 phosphates have 2 phosphorus atoms and 8 oxygen atoms. Additionally, there are 3 calciums in each unit of calcium phosphate. But the coefficient of 3 means that we have 3 calcium phosphate units. So we will have to distribute this 3 to each and every atom, meaning there are 9 calcium, 6 phosphorus, and 24 oxygens in 1 unit of calcium phosphate.